Hello everybody, this is Professor Iris Miano, Math 50 Pre-Statistics. I believe we are on day 7 in our pre-statistical endeavor. We're going to be covering two sections here, 8.2 and 8.3, concerning linear equations, solving equations. What else is on the agenda here? Let's see. One variable, two variables, using them to make predictions, all manner of things. Okay, so let's just go ahead and get right to it. We need to define a few things. Let's define, to begin with, the equation form for a linear equation in one variable. So we're talking about equations. Let's go ahead and add some notes here. I like this color. A plus bx equals c. So that's the basic form that we're looking at here. Generally, there are two constant terms, a and c in this case, so those are representing fixed values, which we've defined earlier. So they're just some numbers. B is also some number, but it's acting as a coefficient on the variable term bx. Okay, so x is going to be the one variable that's being described here. A, b, and c, I'll go ahead and specify, are real numbers. And x is the variable. So in order to find the solution, it's a value that satisfies an equation. How do you know if a proposed solution satisfies an equation? Well, when you plug it in and you simplify both sides of the equation, you should get the same value. So upon plugging in a solution, one should simplify both sides to the same value. And if both sides do not simplify to the same value, then the thing that you plugged in is actually not a solution. Let me show you what I mean in the next examples. Okay, so we're asking, is 4, x equals 4, a solution to either equation? Let's start with this one first. So in order to investigate this, we're going to plug in a 4 every time we see an x. So the first thing we're going to do is multiply that 4 by 3 and then add 5. And we're going to ask, is it equal to 2? You don't have to have the question mark above your equal sign, but it can be a good way to remind yourself that you're not really sure. If this is equal, we're investigating if it's equal or not. Okay? So that is a really kind of a messy looking question mark, so I'm going to rewrite that part real quick. Much better. Okay, so then go ahead and simplify. Well, in order to simplify the left-hand side of the equation, we would multiply the 3 and the 4 and get 12 plus 5. Is 12 plus 5 equal to 2? Well, no, right off the bat, here we can say that this is not going to be equal because we have 17 on one side, 2 on the other. So is x equals 4 a solution to either equation? Here we'll say no, not a solution. Let's see if it's a solution over here. Okay, so now take this other equation, and when you see an x, go ahead and put in a 4, and let's see what happens. Are they equal? Well, multiply the negative 2 and the 4 first to get negative 8. Ooh, this is looking promising, right? Do these end up equaling each other? Yes, they do, because when you take negative 8 and add it to 12, you get a positive 4. So yes. Cha-ching, check, check on that one. So we would say yes, it's a solution. And maybe you're really excited about it, so you put an exclamation point at the end there. Totally optional. Okay. Now that we have some sort of an idea of what it means to confirm if an input value is a solution or not, we might want to know how to manipulate an equation such that we can calculate what the solution is. So enter these properties of equality. The first one being the addition property of equality, which just basically states that any equation you can multiply, you can add. Addition property of equality means you can add the same thing to both sides. So if A equals B, if we have a super very fundamental equation there, you can take that and add the same value to both sides, and it would look something like this. A and B on opposite sides of the equation both have a value of C added to it, and that's fine. Balance is still maintained. According to the original equation, you have simply added a value of C to both sides, okay? Furthermore, you could extend this idea to subtraction property of equality. I'll just call that SPO. This one we can call APO if we're going to acronym this stuff, which I'm totally fine with, by the way. If A equals B, then certainly you could subtract on both sides, just so long as you subtract the same value from whatever was originally there. That's totally fine as well. Where, yeah, C is any real number. Great. Cool. So let's go ahead and solve a couple of equations using either the addition property of equality or the subtraction property of equality, as it seems appropriate, starting with number 1. So the first thing that I would want to do here in solving this equation, and the first thing you want to do with solving any equation, is come up with a plan to isolate the variable. That's what it means to solve an equation. So here I see that the only thing being imposed on the variable at the moment is subtraction of 21. So if I undo that subtraction of 21 by adding 21 to both sides, I'm using the addition property of equality. I'm just adding the same value to both sides of an equation. Now here, I'll notice that these cancel out because I'm performing that opposite operation, which is going to leave me with just x on the left-hand side as desired. And what's negative 9 plus 21? Well, that's going to be 12, right? If I'm not mistaken. 12 and 9 is, 21. Okay, so that'll be good for that one. Box that up. Call it a day. Okay, so what did we do? We used the addition property of equality, or APO for short if you want to. Okay, moving on to number 2. I see this as, a one-stepper. We're going to gather up all of our variable terms. Now notice in problem number 1, our focus was gathering up all the constant terms, so that's what led us to add 21 to both sides, which some people like to think of moving the subtracted off 21 to the other side. That's perfectly fine, just so long as you are performing what is essentially the opposite operation of any type of term or factor, as we'll see in the next property of equality, from one side to another. So here, recognizing that we have a 7x that I want to gather up with the 8x that's on this side of the equation, I want to get all of the x terms together. I will choose to subtract 7x from both sides. Now why is that? Because this term is positive at the moment, so my perceived opposite operation is going to be subtraction. Okay, and that'll be eliminated on this side as desired, and we will have 8x minus 7x will give me 1x. But anytime you have a coefficient of 1, it's conventional just to have it be that single variable. Okay, yes, I could have a 1 here, but it's not conventional, and it's something that we want to get out of the habit of at this level in our mathematical career. And make sure that this 1 that was subtracted off now gets reported as a -1. This subtraction symbol now gets a little bit redefined as a negative sign in front. And that'll be it for that one. Dunzo. So this was an instance in which we used technically a form of the addition property of equality, but it was subtraction on both sides. So I think it's totally fine for us to call this subtraction property of equality SPO or SPO if you're, more into brevity. Okay? Very good. Let's introduce another property of equality. So just like it was okay to add and subtract the same thing to both sides of an equation, it's okay to multiply, which is the outright multiplication property of equality. And it turns out it's also okay to divide both sides by the same quantity. So here's what it would look like to multiply both sides of the equation a equals b by another value thrown in the mix of c, and it's okay to do this so long as c is non-zero. So that's MPO, multiplication property of equality. Now, there's also DPO, division property of equality, which is defined similarly. If a equals b, then a divided by c equals b divided by c. And you can use the same exact caveat. You cannot have a zero c value when you multiply or divide both sides by that c value. Otherwise, you're just going to either zero out your entire equation, which is not very interesting, or you're going to be dividing a number by zero, and we do not entertain that as a possibility. We just call that an undefined value. So again, a, b, and c are real. And furthermore, we'll just call them non-zero as well. Real and non-zero numbers. Very good. Okay, so now we have 4 properties of equality in play technically. Addition property of equality, subtraction property of equality, multiplication property of equality, and division property of equality. So let's go ahead and use any of those 4 in the process of solving these 5 example equations, okay? So it's our job to discern which property of equality is going to be appropriate for solving each equation, and you might have to use more than one property of equality or do some combining like terms beforehand. Looking at number 4 in regard to that last comment. Okay, but focusing on number 1, I'm going to recognize that the variable that I want to solve for, the x, at the moment is being divided by 5. So division by 5 is being imposed on x, and I want to undo that division by 5. So I'm going to choose to do it by multiplying both sides by 5. That will do it. So raised dot, 5 on both sides. Over on the left-hand side, it might behoove me to put that 5 over a 1. Now why? Because I'm multiplying it by a fraction of x over 5. And whenever you're multiplying a whole number by a fraction, it could be advantageous to have that whole number look like a fraction, and you could always do that to any whole number by putting it over a 1. You're not changing the value of that whole number, you're just giving it a new look in order to have it lend itself to very clear slashing away of the common factors that are left. So now you're just going to get an x on the left-hand side as desired, which is going to leave you with x equals what? What's negative 7 times a positive 5? Negative 35. And that's it for that one. Number 2, looking at z being the variable that we want to solve for here, and understanding that it has a fraction coefficient. How do we want to deal with that? A couple of different ways to think about it. What I recommend that you do anytime you have a fraction coefficient that you want to essentially get rid of, you want to turn that coefficient into a 1, you can multiply both sides by the reciprocal of that fraction. So in this case, I'm going to choose to multiply by 7/4. And remember, I can multiply both sides of the equation by whatever I want to, just so long as it's the same number, okay? And everything is going to cancel out beautifully on the left-hand side of the equation. The 4's are gone, the 7's are gone, they all turn into 1's. And the z is by itself. Now what's going on over here, you have a negative 16 being multiplied by a 7/4. Again, like we did over here with the 5 multiplier, it might behoove us to put that negative 16 over a 1, just to be clear about who's in the numerator space and who's in the denominator space for the purposes of the slashing that is possible at this stage in the process. So notice that the 16, albeit negative, is sharing a common factor with the 4, essentially the 4 itself. So 4 divides itself the once, 4 divides 16, or rather negative 16, 4 times, and don't forget that the negative sign is in play, okay? So you're going to have z equal to, what's negative 4 times 7? That'll be negative 28. And you're done with that one. So far, they've been more or less one-steppers. This will be true also for number 3, and number 3 is quite tricky. It's actually one of those problems that's so easy it's hard. You may be thinking to yourself, well, this one's pretty much solved, right? Like x is already by itself. Not so fast. It has technically a -1 factor in front of it. So you want to get rid of that -1 factor, and how will you do it? You can either multiply both sides by -1 or divide both sides by -1. So I'm going to choose to divide both sides by -1. And that's how it'll look. In doing so, I can cancel out all of the previous negativity, like so, and like so, on both sides of the equation. And then I will be left with x equals 9 over 1, which is just a 9. Okay? So this is what you must do when you come across an equation that's either partially, solved. If you come to a step in your process where you've got it all the way whittled down to negative x equals some number, you're going to have to account for that -1 factor out in front of the x before you can call it all the way solved, okay? So that's one time it can get pretty tricky. Moving on to number 4, I recognize that there is the necessity of combining like terms on the left-hand side before we get started with this process. So what is 4r minus 9r going to give us? Well, that'll give us -5r. It's equal to 20. And now it's our job just to recognize that we need to get rid of that factor of -5 in front of the r. So we're going to divide both sides by -5. On the left-hand side, the negatives will cancel, the 5s will cancel. We're going to essentially just be left with r as desired. Here, though, on the right-hand side, we need to recognize that there's a common factor of 5. It divides itself the once, it divides the 24 times, and don't forget, this ultimate value of what's happening on the right-hand side will be negative, okay? So cleaning house here, with everything already simplified and just seeing what's left, it'll be r equals -4. I know what you must be thinking. Isn't this 4 over -1? Sure, technically, but you want to uphold conventions with writing your final answer, taking any negative signs and pulling them out in front. And if you have any fractions whose denominator value is 1, just go ahead and knock out that denominator value and represent it as the integer that is actually being in play here. Now here for number 5, we have a very special situation in which there are actually 4 correct ways to move forward, using first either the addition property of equality or subtraction property of equality, and then we'll use either multiplication or division property of equality subsequently. So what I mean by that is you can either subtract 4x from both sides, add 5 to both sides, subtract 6x from both sides, or subtract 9 from both sides. All 4 of those initial steps are completely valid. Personally, I tend to focus on gathering up all of the variable terms first, and I do so in such a way that will lend itself to a positive outcome. So in that regard, I'm choosing, and this is a stylistic choice here, to subtract 4x from both sides. That will eliminate all of the x's from the left-hand side and gather them all up to the right-hand side. Once you make that decision, the subsequent steps that are most effective, most efficient in the process of solving the equation will fall into place, okay? Like by that, everything else is bespoke, it's predisposed, it's it has to go in a particular order in order to be efficient. Okay, so by that I mean the next logical step would therefore be subtracting 9 from both sides, getting all of the constant terms gathered on the left-hand side of the equation. Okay, so that'll give us -5 minus 9 will be -14 equals 2x. And then lastly, we can divide both sides by 2. And that will allow us to slash away the 2's. We'll get just the x on this side. The common factor of 2 divides itself the once, it divides 14 7 times, and we are still negative here. So that'll give us a final answer of -7 equals x. And if you don't like the way that reads, of course, you could just give it a pancake flip. Call it x equals -7, because all equations are symmetric. You can read them backwards or forwards, and they're still going to mean the same thing. Okay, now before we move on, I thought maybe I would go back to the original 5 problems and actually state all of the properties of equality, at least their acronyms. I'll do that in teal, that I used here. Here, I multiplied 5 on both sides of the equation, so I used MPO, multiplication property of equality. Here, again, I used MPO. I multiplied the reciprocal on both sides of the equation. Here I used depot. I divided both sides of the equation by -1. And then over here I combined like terms, and then I used a little bit of depot. Maybe I'll say here I combined like terms, CLT if you like. I just made up that acronym right now. Here I'm using a little bit of subtraction property of equality, once, twice, and division property of equality to wrap things up. Okay, it's not necessary that you use these acronyms and label them as you go. I just wanted to give some sort of context as to why we care about learning these properties of equality, because whether we realize it or not, we are using them to manipulate elements of an equation in order to isolate the variable, which is the process of solving an equation. Moving on to the next part of this first section that we're going to cover, we're going to practice more translation problems. You can never get too much practice in this regard, and translating English into mathematics is an incredibly important skill for us to hone over the course of the semester. We're going to be revisiting this quite a bit over the course of the semester. So here we go with another endeavor in this regard. So in this example, a couple of examples, we're going to translate the English phrase into a mathematical expression and then simplify the expression. We're going to write both the original expression and the simplified version as well. So let's just start with number 1 and directly translating it, okay? Anytime you see a number, okay, you can translate that into any variable that you want to. I'm going to stick with the generic quintessential variable, and that's x, okay? A number. Then we're going to subtract, because that keyword of minus alludes to subtraction. And then what are we subtracting? The difference of 8 and a number. So whenever you subtract or add a difference, or you're multiplying by a difference or a sum, that means you got to put up some parentheses, okay? So the difference business, that is going to be not only having subtraction inside, like the difference here, but it's also going to be warranting the use of the parentheses. Because there's an operation in front of this difference, we need to have parentheses encapsulating the subtraction associated with the difference, and then separating it from the minus that was mentioned beforehand. And what is the difference that we're trying to reflect inside of these parentheses? It's the difference of 8 and the number. So use that same variable again that you picked originally, in my case, x. Does everybody see how that went down? Between 8, let me go ahead and point this out here, and the number, should be the same variable that you chose ahead of time. Okay, so this is going to be that first direct translation. And then, of course, we need to come up with the simplified expression, which is to say, I'm going to go ahead and rewrite the expression 8 minus the quantity 8 minus x, which is going to have, in regard to simplifying, we need to distribute through this negative sign, changing this the sign and operation of everything inside of the grouping, which will give us x minus 8, and then now plus x. So combine your x terms here. This one and this one can be combined, and so it'll turn out that we have 2x minus 8. And then that gives your second part of the answer, the simplified expression. So here's the original directly translated expression, and here is the simplified version over here. Okay, let's do the same thing, but with example number 2. Let's go back to the teal color in order to translate it. So we're going to go with 3 times the sum. Times the sum, huh? So we're going to have implied multiplication by just resting the 3 next to a set of parentheses. If you want to put a raised dot right here, it's not wrong to do that. I'm going to make a stylistic choice and not have a raised dot though. And if we're going to have times the sum means that there's a plus sign in here. Times means that we're going to have not only no operation right here, but also the parentheses. And what is the sum? It's the sum of the number, okay, that's going to be this little guy right here, and 5, which goes in this position. Cool. So that's the direct translation. 3 times the quantity x plus 5. Simplifying, we need to distribute through the 3. I'll rewrite it. And then in this green color, I'll outline the distribution that I mean to make in this first simplifying step, and that'll become 3x plus 15. And that's as far as I can simplify it. The 3x term and the 15 constant term, they are not able to be combined. Yeah, that's the color I wanted. So again, here's the original directly translated expression. Here's the simplified version of that. And that'll do it for those 2 examples. Let's also tackle a couple of percentage problems, and then I think, yes, we're done with this first 8.2 section. Here we go. In 2013, the sales of Monster Energy drink were $3.1 billion, which was about 35% of all energy drink sales. What are the total sales of all energy drinks? Okay, this is a pretty tricky problem because we need to understand that the previous drink sales were, which was about 35% of all energy drink sales. Okay, so what are all energy drink sales? Well, this 3.1 billion, okay, and we could just take the 3.1, go ahead and change the color here. Okay, so this was, we're going to translate was as the past tense of the form is, and is translates to the equal sign. Okay, so this 3.1 billion, we're going to leave it in terms of billions of dollars just so it's easier to work with. Was about 35%. What's 35% as a decimal? Because we need to turn that percentage into a workable form. So decimal form would be good there. Move the decimal place over 2 spots to the left and throw out the percentage sign. That's the conversion that we need. Of translates to multiplication, right? Sorry. Woo. Here we go. All energy drink sales. Okay, so really all energy drink sales is going to be our unknown. So just to be clear, this 3.1 billion was 3.1 equals $3.1 billion was about 35% of multiplication. I'm representing that with a raised dot. All energy drink sales, that's X, that's our unknown. So what we've done here is we've picked apart the first sentence of this percentage problem in order to translate it into an equation. Now, let's answer the second sentence in this prompt in order to, by solving the equation, which is essentially just divide both sides, let's do this in this green color, I guess, by the coefficient of the x. You're going to need to reach for your calculator here, okay? So let me get the red out. That'll just slash over here. So essentially you're going to go 3.1 divided by 0.35. Okay, so calculator's totally fine for this. 3.1 divided by 0.35. Okay, so I'm getting 8 point. So what color am I on? Let's go back to this purple color. X is approximately, and this is what my calculator is giving me, 8.85714,286. Obviously, I don't need all of this information, okay? I just need to uphold the convention that's already been established here. We had billions of dollars rounded to the nearest one decimal place. So let's go ahead and do that as well. So let's round this number to one decimal place by, oops, I want to actually do this in pink. Focusing on the one decimal place there, but checking in with the neighbor. Ooh, neighbor, you're a 5. So you're going to bump this 8 in the 10th place, excuse me, up to a 9. So our final answer should be, let me do this back, $8.9 billion. But let's go ahead and put that in the form of a sentence. The total sales of all energy drinks was this, $8.9 billion, period. Okay, and that'll do it. Let's do this direct translation one more time, but with this other example here. It says in 2010, there were 223,000 new cases of lung cancer, which was about 14.6% of the new cases of all types of cancer that year. How many new cases of cancer were there in 2010? So let's probably do this in a little bit of a better order. Let's go ahead and let X, and you can choose different variables if you want. If you're like, X is too boring, I want to say C for cancer. I mean, by all means, pick a more descriptive variable if you want. I'm going to choose X though, stylistic choice, totally fine. X equals the new cases of cancer. Because remember, the 223,000 is just lung cancer, okay? So we want to figure out how many new cases of all different types of cancer there were, recognizing that this 223, and we'll have it in thousands of new cases, was 14.6%. Hopefully everyone can follow how this decimal, right, is representative of 14.6%. It's the decimal representation of that percentage of new cases. Okay, so again, pretty much same setup as the previous problem. We are just going to divide both sides by the 0.146. Okay, slashy slash, we'll get X by itself here, and we need to reach for our calculator here. Okay, so again, here we go. I'm going to type in 223 divided by 223 divided by 0.146, and that'll be 1,000. X is approximately 1,527.39726. Okay, more numbers than I need, but what are we going to do with this? Well, recognize that this was in thousands of new cases, and it was rounded to the nearest 1,000. So let's go ahead and round this to the nearest whole, number, basically, is how we want to translate this. So, nearest whole number, focus on the ones place and round it. Since the next digit over is a 3, that 7 is just going to stay put. And then there's one more piece of interpretation that we really should do in order for this to read correctly, right? Because it's supposed to be this many thousands. So that means if we wanted to write this number in standard form, it would read as follows: 1,527. And then if this is in thousands, you need to put 3 more zeros after it. Well, what does this number look like? Well, this is 1,527,000. Okay, so we can actually change the unit here and have it in millions of new cases. I think that would be appropriate here. Now, how would you know that this is the thing to do or the thing you should do? Well, basically it's just experience. And so you seeing me do this hopefully is going to have you guys recognize that it's okay for you to do this, to change the unit a little bit slightly, just so that it reads better and makes more sense to the objective reader, okay? So we'll say that the number of new cases of cancer in 2010 was, we'll say, 1.527 million. And that'll do it. That'll be sufficient. Okay, so I'll go ahead and kind of box that up to make it distinct from some of the work that we did over here. I'll also box up the previous problem. Okay, great. So let's go ahead and I'll save that. And we have one more section to cover here. We're going to be solving some more equations, and they're going to get markedly more complex. Nothing we can't handle, though. Let's go ahead and put the add notes business on here. And we'll start off with this electric blue. Now, the idea with solving equations is the same thing that we were thinking about with the previous equations that were a little bit more simple. But the idea hasn't changed at all. And it is to isolate the variable using properties of equality. Oops. Properties of equality. Furthermore, we might need to use distribution and combining like terms. Okay. Handwriting is getting more and more terrible as we go. All right, but let's go ahead and tackle this. I'm going to start by distributing, and I'll use the orange here. This 2 over the quantities there. We need to distribute this negative sign over this quantity here, and the 5 over this quantity on the right-hand side of the equation as well. So lots of distribution. And you know what? We can do it all at the same time if we feel comfortable with it. So performing all the distributions all in one step, we would get negative 10x minus 6 minus 4x plus 1 equals 5x plus 10. Okay? Combining like terms on the left-hand side. X terms get combined, constant terms get combined. I'll do them in straight underlines versus squiggles. By no means is this notation necessary, but can be kind of fun. So this will give us negative 14x altogether minus 5 equals still 5x plus 10 on the other side. And now since we have one variable term and one constant term on both sides of the equation, this is when we can have 4 different correct ways of moving forward. I'm going to go ahead and stick with what I usually do, which is to add, oops, excuse me, getting ahead of myself there. I'm going to add 14x to both sides. Why would I do that? Because that way I treat the variable terms first, and I'm going to get a positive result when I do this to both sides of the equation, at least for the x's. And then we'll see what pans out for the constants. So that'll be negative 5 equals 19x plus 10, and then next we will, oh, keep it a blue, subtract 10 from both sides. And oops, I guess if I'm trying to be consistent, I would have a red slashy there. And then we will have negative 15 equals 19x. Lastly, we will divide both sides by 19. And that'll give us x equals negative 15/19. Believe it or not, there's nothing left that we can do to simplify this. 15 and 19 do not share any common factor, so it cannot be reduced any further. Okay? Notice that it maybe in the previous step when I argued that the negative sign was in front of the 15, I pulled it out in front of the entire fraction because aesthetically speaking and conventionally, it is imperative that we recognize that the entire fraction is deemed negative. Okay? Cool. Let's do this next one right here, which got a little bit crowded by my previous work. We'll just try to ignore that for the moment and recognize that this equation is riddled with fractions, but notice that the denominators all seem to have a common denominator option that's relatively simple for us to follow. Okay, so what is the LCD here? The LCD, and I'll go ahead and kind of just draw a line here. The LCD for this problem is 8, right? And what's great is that this particular fraction right here already has a denominator of 8, so we actually don't need to build up that fraction at all, but we're going to multiply this, I'll put it in red, fraction by a fun one of 2 over 2. Is everyone okay with that? It's just a factor of 1 that I'm multiplying it by so that I can force this fraction to have a denominator of 8, the LCD. This one, I'm going to multiply it by a 4 over 4. And this one I'm going to multiply also by a 2 over 2. And in doing so, here's how those fractions will be reevaluated. So here I'll have 10/8 plus, or, you know what I could do? Rather than doing it this way, actually, hold on. I'm going to do this a little bit of a different way. I'm going to multiply both sides of this equation by the LCD so that I don't have to deal with fractions at all. Check this out. You're going to like this even better. Okay, so this is good. Let me again, give myself some space there. If I multiply both sides by 8, so this is another way to think of it. Multiply by 8 over 1. That's supposed to be a raised dot. Multiplied by 8 over 1 here. Now why 8 over 1 rather than 8? Well, everything that I'm going to be distributing on both sides is going to be having a fraction component to it, so I might as well think about this 8 factor that I'm multiplying both sides by as a fraction. So in distributing it here and there, here and there, I know it's getting a little messy. I'm going to show you what I mean. 8 over 1 gets multiplied by the 5/4. Then I add 8 over 1 times 9/2 x equals 8 over 1 times 3/8 x minus 8 over 1 times 1/4. So you see how every single component on both sides of the equation just got a 8 over 1 multiplied by it. So I'm circling them just to show you where they all are. If I took out all of these circled bits right here, I would have the original equation back again. So it's just that everyone got multiplied by an 8 over 1. And now I'm ready to slash. Oh my gosh, so much fun. So for each individual term, go ahead and slash away the common factors. And you'll get the following things left over. And since we multiplied both sides by the LCD, there's not going to be any more denominators. See how all these denominators ended up turning into 1s? That is by design. We want that. We did that on purpose. So now for each term, look at what factors are left. Here in the first term, we have 2 times 5 left. That's 10. Plus 4 times 9 times x. That's 36x equals 1 times 3 times x, it's 3x, minus, don't forget that signage is there, that operation, 2 times 1, that's just a 2. Okay? Now we have something way more familiar to work with here. Let's go ahead and subtract 3x from both sides. Again, stylistic choice there. You could have done 3 other things, which would have been totally fine as well. Okay, let's go ahead and subtract 10 from both sides. 33x is equal to negative 12. Divide both sides by 33. And it looks like we have a common factor of 3 we need to divide out. So that'll be giving us what? Well, the 33's go here. We're left with x. We're going to stay negative, but there is a common factor of 3. So divide out the 3 from 33 and you're left with 11 and 4 in the numerator there. So your final answer will therefore be x equals negative 4/11. Great. Fantastic. Okay, so a little bit of review on some more complex equation solving. Just remember your properties of equality, how to distribute, combining like terms, and you should be good to go. Oh, we have one more that we're going to tackle before we leave. I would again do the LCD thing. So let me go ahead and put a darker color. LCD is 12 here. I'm going to multiply both sides by 12 over 1. Right? And why 12 over 1? Because everything that I'm multiplying both sides by is, a 12. So I'm going to go ahead and do it here and there. And then the multiplication will just lend itself nicely there. So 12 over 1 times 2p plus 4. I think it's imperative to put the binomial numerator in some parentheses there just to make sure that everything gets dealt with properly. That'll be 5p minus 7, again, parentheses on that one, over 6. And that's equal to 11 over 12 times 12 over 1. And then now it's slashing time. The 12 and the 3, they have a common factor of 3. 3 divides itself to once, divides 12 4 times. And then over here, so then this 4 will then be distributed there and here. Well, we could save that for another step though. The 12 and the 6 here have a common factor of 6, left over a factor of 2. That will eventually get distributed there. The 12s outrightedly cancel on this side. So if we're feeling comfortable, we could do this distribution all in the next step. And if you like to see that, it'll be 8p plus 16. And then again, it's not just, sorry, the 2, it's a negative 2 that gets distributed. So that'll give you a negative 2 times 5p will be a subtracted off 10p. Negative 2 times negative 7 will be a plus 14. And then everything cleaned up over here will just give you 11. We have like terms we need to combine. The p's, the constants. On the left-hand side, this is looking very familiar from the previous problem. We'll have negative 2p plus 30 is equal to 11. Let's go ahead and subtract 30 from both sides. And what do we get? Negative 2p is equal to, what's 11 minus 30? That's 19. And it's negative. So then we divide both sides by negative 2. Get rid of it on this side. P equals negative 19 over negative 2, which settles down to 19 halves, which you can call what? 7.5? No, 9.5. Not that you need to. P equaling 19 halves is perfectly fine. There's a final answer there. Whew! So fun. All right, I'm happy to go over that in more detail. I did kind of go through some of the algebraic complexity, or details rather, a little bit more quickly than some folks might have liked, okay? So let's go ahead and switch gears over to a percentage problem. All right, now this can actually get quite complex. So let me make sure I'm doing plenty of translation here and making it clear. In 2013, the mean annual per person consumption of butter was 5.5 pounds. Wow, that's a lot of butter. But if it's over a year, I guess it's kind of okay. Up by 12.2% from 2010. What was the mean annual per person consumption of butter in 2010? Well, okay, that's going to be our unknown, mean annual per person. Oh Lord, what a huge label this is. Consumption of butter. Meant to be confusing. Okay, let's just say to ourselves we need to figure this out for 2010. All right, this whole thing is our unknown, and we're going to relate that to the 5.5 pounds, right? This 5.5 pounds is always means equal sign, is 12, oops, sorry. What's a 12.2% as a decimal? This is, sorry, 0.122 as a decimal, but this is an increase, a percent increase from what was happening in 2010. So remember what we do for percent increases? We add 1 to this in order to have a multiplier of 1.122 times x. So we need to divide both sides by this multiplier. In order to get the value of x. So this is where you can, again, reach for your calculator. 5.5 divided by 1.122, and that is going to be approximately 4.90196078. More than enough significant figures here. More is always better before you do any rounding. So what do we want to do here? Well, they have their pounds. The convention is to have only one decimal place, so we're going to do the same thing. Luckily, rounding to that one decimal place is really easy because the neighbors is 0. So that'll mean that the mean annual per person consumption of butter for 2010 was 4.9 pounds. Yikes. And why are we okay with it being less? Well, this 5.5 pounds in 2013 is supposed to be a 12.2% increase from what was going on in 2010. So we should expect that the 2010 value to be less than the 2013. Okay, let's do this one more time, but with a different scenario. In 2016, the number of people visiting Reno was 14,375. This, the 14,375, is an increase. So take this 5.7%, which is 0.057 as a decimal, add 1 to it, and then that'll give us the multiplier that we want. For the number of people visiting Reno in 2015, we're going to let that be x, okay? So 1.057 times x. Divide both sides by that multiplier, 1.057. 1.057. Reach for your calculator. Type in 14,375. And then divide by 1.057. Yep. And we will get 13,000. X is approximately 13,000 599.8108. Remember, context is important here, people. And what are we talking about? What is this number for x supposed to be representing? Well, it's the number of people visiting Reno in 2015. Should we be reporting fractions of people? No, we shouldn't. So we should always be rounding to the nearest whole number. And this situation is going to dictate that we have to tack on an extra unit to the 9. But what's the number after 9? 10. Oh boy. So we have to add another value to the next place over, the 9, which is going to have to come and turn into a 10 as well. And so we're going to have to carry that over to the 5. And that's where we can stop. So the rounded to the nearest whole value of this particular number is going to be 13,600. So this is the number of people visiting Reno. So 13,600 people visit Reno in 2015. There you have it. Let me know if you have any questions about that one. There's just, I think, 1 or 2 things that we're going to cover here. Ooh, okay. Kind of. Okay, this one's going to be relatively quick here. When you solve a system of equations by graphing, you're going to basically solve both of the equations for y and set them equal to each other. And that's what the setup is here, folks. Okay? So the idea is to solve for x when linear equations in 2 variables are solved for y, one thing, and then also set equal to each other. Okay, so notice that these 2 equations, y equals 2x, 2/3 x plus 14/3, that's the red trajectory here. And then the other equation, y equals -3/2 x plus 5/2, okay? So they are graphed on the same coordinate plane, and notice that they're both solved for y, right? It's y equals blah-de-blah, and y equals this other blah-de-blah. So we took the 2 blah-de-blahs and set them equal to one another. And in doing so, you can find the x value that is the intersection point right here, okay? So this is the thing we want to capitalize on, is saying this will give you and the x value of -1, right? Because that's where it lines up on the x-axis, and then the y value of 4. So that means this means, well, it'll be the point that's the solution to both lines at the same time. So consider, when is a point a solution to a line? A point is a solution to a line when the ordered pair satisfies the equation. That's all I really want you to put here. Furthermore, what point would satisfy both lines at the same time? It's going to be the intersection point, which we have here, which is at -1, 4. -1, 4. That's the ordered pair that represents this intersection point. And so that's what I want you to report for the second bulleted point right here. Okay, great. We're going to get into more detail on that somewhere else later on in the semester, so I just wanted to touch on that very briefly. And then we're going to wrap things up with a little bit more to say about linear models. So linear models are the equations of the form y equals mx plus b. Does that sound familiar? It should. M is the slope. And b is the y-intercept, which is just a fancy way of saying the place where the line crosses the y or vertical axis, okay? Now you might not necessarily use x and y to represent your independent and dependent variable respectively. You might use other letters. A case in point, this example that we're going to use here. We're going to find the minimum salary for a hockey player in National Hockey League, okay? So it was $500,000 in 2010, okay? And it increased about $14,000 per year until 2015. Let S be the minimum salary at T years since 2010. Okay, so S is going to be acting like our Y value, like our output, because the salary is dependent on how many years you've been working as a hockey player, right? Okay, so we're going to have a much more in-depth conversation later about independent and dependent variables. The independent variable is like x as you've ever known it in linear equations, and the dependent variable is very much akin to like y. In this case, S is acting like the dependent variable, so kind of like y, the output, and T is acting like x, or the independent variable, or the input. All of these terms are synonymous with one another, which makes it extra confusing, okay? So don't worry, we'll have plenty of discussion on this. Let's find an equation of a model for the player's salary. Okay, like I said, S is going to be like the y, and that's equal to the slope is going to be associated with the change per unit of time, or whatever is associated with the input variable. So that's going to be your 14,000. So if we have 14,000 increase per year, so that's a positive 14 is going to need to be the multiplier on the T. Okay, and then also the minimum salary, that's your starting place. You need to have that to begin with, so that's going to be your fixed value, also known as your y-intercept, or in this case your s-intercept, because the vertical axis is going to be associated with the variable s. How did I come up with that so quickly? Well, it's really a matter of experience. So I can get into more detail about this in a lecture if you'd like, but just so that I don't make this video too long, I'm just going to go ahead and go forward with estimating the minimum salary in 2015. So 2015 is how many years since 2010? So that means T will equal 5 in 2015. So really we're like, what is the salary? And notice that my S's are fancy. I do that so that they don't look like 5s, because look, my 5 looks totally like an S, right? But if I do these little extra lines, then it's hopefully nobody's making any errors in thinking my S's are 5s. But plug in a 5 for T, because 2015 is 5 years past 2010. And then you can go ahead and reach for your calculator and say, what's 14 times 5? Well, that's 70, plus the 500,000 that's initially there. It's 17, sorry. It was 70 plus 500 is 570. Okay. 570, and that's in, we're in thousands of dollars. Okay, so minimum salary in 2015 was $570,000. Cool. Last one. Estimate the minimum salary when the minimum salary was $550,000. So that's when you have your S value is supposed to be equal to 550. And you're going to have that equal to the rest of the linear equation, which is 14t plus 500, and you're going to solve for t now. So in doing so, we're going to have to subtract 500 from both sides, leaving 50 equals 14t. Divide both sides by 14. Go ahead and reach for your calculator, and t is going to be approximately what? Well, 50 divided by 14, it's not going to divide evenly. So we'll get t is approximately 3.57 1428, blah, 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 blah. So it's about 3.5 years. Well, 3.5 years after 2010, because that's what t is supposed to be representing, is going to be, you know, mid 2013, right? Cool. So we would say minimum salary was $550,000 at about mid-2013. Okay, folks, thank you so much for your attention. That's it for today. Plenty of instances in which we could go in some further detail. So hopefully you've been following along with your notes and are writing down questions as we go, so we can get into the details necessary in order to have all of this stuff really landing. Okay? Cool. So let's go ahead and talk about it. Thanks a lot, guys.